Salam and good morning to Dr. Azidin and my friends. My name is Sawtooth and my group mates Loo Wei Jun and Yap Zhi Xuan from BKG Year 3, Section 3/2. Today we will present assignment 2 of Industrial Power Electronics. In this assignment, we have to design a switch mode power supply that produces a variable DC output voltage of 0 volt to 50 volt, where from a single phase AC input voltage of 240 VRMS with 50 Hz. The output power is 50 watt and the output ripple voltage not exceed 5%. We had to calculate the duty ratio, inductor, and capacitor values and compare it with the simulation result by simulate with MATLAB simulating software. This is our design for the Smps, where we start with a transformer which has a winding ratio of 12:1 with 2 secondary windings. The transformer has stepped down the single-phase AC input voltage from 240 VRMS to 20 VRMS for one winding. So for two windings, we will get 40 VRMS and we times with square root 2 and we will get the V in is 56.569 volt. And next, there is a full wave rectifier circuit to convert AC voltage into DC form. And a capacitor is to provide a smooth DC output voltage with free ripple. This can keep the DC output voltage constant to protect the buck converter. From the requirement, we can calculate the condition of the buck converter. Besides that, we set our switching frequency as 40 kHz. Then we can find the duty ratio by V out divided by V in, and we will get the minimum duty ratio is 0 and the maximum duty ratio is 0.8839. To find the resistor, we use the equation of the power, which is V squared divided by resistor, and we rearrange the equation. We can find the resistor is equal to 50 ohm. For the inductance, we find the minimum inductance by the equation, and then we times with 10, and we will get 0.725 millihenry. To find the capacitance, we use the ripple equation, where the ripple is 5% and is equal to 0.05, and we rearrange the equation, we will find the capacitance, which is 0.25 microhenry. To find the inductor current, we find the maximum and the minimum inductor current, and we find the difference, and we can get the average of inductor current, which is 0.28. And lastly, the output voltage ripple, we calculate and we get 2.5 volt. That's all from me, and I pass to my friend.
My name is Loo Wei Jun, and now I will show how to determine the stability of the converter. So at my right side, this is the block diagram to determine the stability. So at first, we need to do the calculation first. We choose the S, which is the 0 at 1000, and Ki gain at 25. By using the formula Ki over Kp equal to S, we will get the Kp equal to 0.025. So for the setup, we set the gain first, which is Kp equal to 0.025, Ki equal to 25. And we run the model linearizer and we'll get the plot for this. So for the magnitude plot diagram, we will get 1.83 kilohertz at 0 dB. So is the crossover frequency is considered stable because it is less than the switching frequency, which is 40 kilohertz. So in order to determine the phase margin, we will get the phase degree equal to 167 degree at 1.83 kilohertz frequency by using the formula 180 degree minus 167 degree will equal to 13 degree. It is considered not stable because it is not in between 30 degree and 60 degree. So we also perform the pole zero map, and from the pole zero map, all of the zero and the pole are at the left half plane, so it is considered stable. However, overall, it is considered not stable because the phase margin is not stable. So now we need to improve the stability of the converter. So we must make sure the phase margin is at 45 degree. So at the bot plot, we will get 16.1 kilohertz frequency at 45 degree phase margin. So at the magnitude diagram, at 16.1 kilohertz frequency, we will get 39.3 dB. So by doing the calculation, we need to move up to 30.3 dB. So this is the previously Ki and Kb. We will need to get the value first. By using the formula 20 log 25, we will get 27.9588. By adding the old one and with the new one, we will get 67.259. And again, we substitute the formula and we will get the Ki equal to 2306.43. And we sub this Ki value to get the Kp value, and the Kp value we will get 2.306. And again, we need to change the parameter first. So for the Kp, we need to change to 2.306, and the Ki is 2306.43. So we run the model linearizer again. So this is the mod plot for this, and at the 0 dB, we will get 16.1 kilohertz. So is also the crossover frequency is considered stable because it is less than the switching frequency, which is 40 kilohertz. So in order to get the phase margin, we will get 135 degree at 16.1 kilohertz. So by using the formula 180 degree minus 135 degree, we will get 45 degree. So it is considered stable. So we also perform the pole zero map. Since all of the pole and zero is at the left half plane, so it's stable. So overall, this converter is stable. So that's all for me. Thank you.
Salam sejahtera and very good day to my lecturer, Dr. Azidin, and my fellow friends. My name is Yap Zhi Xuan, and today I'm going to proceed with the next part of our presentation for assignment 2, which is the presentation of waveforms of our SMPS controller from MATLAB through simulation. So first, here will be the circuit for our SMPS controller. And as explained by my group members earlier, we are going to use a 12:1 winding ratio transformer at the input of our SMPS controller. So basically this transformer is going to step down the input voltage of 240 VRMS to just 40 VRMS, and when we convert that 40 VRMS into peak voltage, it will be around 56.56 volt. So here we are going to insert a DC voltage source of 56.56 at the input of our buck converter itself. And next we're going to have a look at the sawtooth signal. For the sawtooth signal, we are going to use a frequency of 40 kilohertz, and here will be the waveform of the sawtooth signal itself. Okay, next we are going to have a look at the reference voltage of the Smps controller. So our reference voltage is around is from 0 to 50 volts. So the reference voltage will change from 0 to 50 volts at second number 2, at the second, and it will change from 50 volt back to 0 volts at the fourth second. Okay, so now first we're going to have a look at the output voltage waveform of the Smps controller as well as the inductor current. Okay, so basically here will be the waveform of the output voltage and also inductor current. The waveform on the top here will be the inductor current waveform, and the waveform at the bottom here will be the output voltage waveform for the Smps controller. First we are going to have a look at the inductor current first. So now let me zoom in the inductor current. Okay, now let me change it to current. Okay, so first we are going to move the cursor and cursor 1 and cursor 2 around so that we can have a look at the minimum inductor current as well as the maximum inductor current. Okay, so cursor 1 here will be the minimum inductor current, which is around 0.9 ampere, and cursor 2 will be the maximum inductor current, and the value will be around 1.1 ampere. Okay, next we are going to have a look at the voltage waveform of the Smps controller. So similar like just now, we're going to change this to voltage measurement and we are going to change the position of the cursor 1 and cursor 2. Cursor 1 will be the maximum, cursor 2 will be the minimum. Okay, so as we can see here, the changes in output voltage of the Smps controller will be around 2.3 volts. Okay, and when we convert it into percent, we can obtain the output voltage ripple of the buck converter itself or the Smps controller. Okay, and when we zoom out output voltage waveform, okay, we can see that the output voltage here changes from 0 to 50 volts at the second, and the output voltage waveform changes back from 50 volts to 0 volt at around 4 seconds, which is exactly the same as our reference voltage just now for our circuit. Okay, next we're going to have a look at the gate signal for the Smps controller. Okay, so here will be something like that, and we have to zoom in on the waveform to have a clearer look. too big. Okay. Okay, so as we can see here, whenever the, okay, so first of all, you can see three waveform lah. Okay, the first we have a look at the two waveform at the bottom here. The yellow color one will be the sawtooth signal waveform. The blue color one will be the feedback signal waveform for the SMPS controller, while the yellow one on top here will be the gate signal waveform itself. Okay, so whenever we see that the feedback signal is greater than the sawtooth signal, the gate signal will be high. And whenever the sawtooth signal is greater than the feedback signal, the gate signal of the MOSFET will be low. Okay, so whenever the gate signal is high, the MOSFET will be turned on, and whenever the gate signal is low, the MOSFET will be turned off. Okay, so we can actually have a look at the duty cycle of this buck converter by measuring the on time and also the period of the gate signal. Okay, so the on time of this gate signal will be of the gate signal will be approximately 21.584 microsecond, and the period will be 24.8 microsecond. So basically we divide the on time of the gate signal by the period of the gate signal, we can obtain the duty cycle, and this will be compared later on with the calculation later on of during my presentation. Okay. So lastly, we are going to have a look at the diode current of our SMPS controller. So it will be something like this, and we know that theoretically the diode current will only flow whenever the switch or the MOSFET is switched off. Okay, so whenever the circuit is switched off, the diode will be in forward bias, and the inductor will releases its energy. So there will be flow of diode current through the inductor, and basically the inductor current will be equivalent to the diode current. So this part will be the time when the switch is switched off. Okay, so let me zoom in on the waveform here. Okay, so the diode current is something like this. Okay, so inductor current will be equivalent to the diode current. So here the maximum diode current here is at around 1.1 ampere, which is exactly the same as the maximum inductor current. And for the minimum diode current, it will be around 0.9 ampere, and again it's almost the same as the minimum inductor current. Okay, so next we're going to proceed back to our slide. Okay, we're going to have a look at the comparison between the simulation and the calculation result for the buck converter as well as the SMPS controller. So for the duty ratio, through calculation, we can calculate that the duty ratio is around 0.8839. However, for simulation, we obtain a duty ratio of 0.864, and there's a percentage error of 2.25%. For minimum inductor current, the minimum inductor current through calculation is around 0.9 ampere, while for simulation it will be around 0.9041 ampere, and there's a 0.46 percentage error. For maximum inductor current, for calculation we obtain 1.1 ampere, however for simulation we obtain 1.101 ampere, and that's a 0.0909% in percentage error. For changes in the changes in inductor current, the calculation we obtain is 0.2 ampere, while for simulation we obtain a value of 0.1972 ampere, which is around 1.4% percentage error. And lastly, peak-to-peak ripple voltage, we obtain 2.5 voltage from calculation, while for simulation we obtain a value of 2.363 volt for peak-to-peak ripple voltage, and that's a 5.48% error. So as we can see here, the calculation and simulation results are approximately the same. There may be some differences um, due to the assumption of ideal components when we are calculating these parameters during calculation. Okay, so in general we can conclude that the main objective of this assignment 2 has been achieved, as the Smps controller that we have designed provide a well-regulated output voltage according to the reference voltage, which is from 0 to 50 volt. So that's all from our group. Thank you so much.